Hi everyone, I am Gopika A.S., Assistant Professor of Civil Engineering. It's an IT ADU. Today I am going to discuss here about a topic from Geotechnical Engineering, that is measurement of shear strength. The determination of shear strength of a soil involves the plotting of failure envelopes and evaluation of the shear strength parameters for the necessary conditions. The following tests are carried out for this purpose. The laboratory tests are direct shear test, triaxial test, unconfined compression test, vane shear test, torsion test and ring shear test. The field tests are vane shear test and penetration test. So, we will discuss what is direct shear test. It is the oldest shear test still in use and it is quite simple to perform. The soil specimen that is to be tested is confined in a metal box of square cross section that is split into two halves horizontally and a small clearance being maintained between the two halves of the box. The test is also called shear box test. And there is no control over drainage conditions and no mechanism to measure pore pressure. Hence, the test is preferred for drained condition. A constant shear strain rate of 1.25 mm per minute is applied, and there is two types of application of load are possible. That is, one in which the shear stress is controlled and the other in which the shear strain is controlled. Generally, shear is applied at constant rate of strain. The normal stress and shear on the failure planes are obtained by dividing the normal force and shear resistance of the soil is recorded by proving ring dial gauge at failure. This is the arrangement for direct shear test, and in this figure we can see that the proving ring and the square box, that is called a shear box, and in the longitudinal direction we apply the shear force and the soil sample will get sheared and the value can be, or the number of divisions can be measured from or read from the proving ring reading. The values of shear stress are plotted against effective stress for each test. From the graph we can determine that in x-axis it is effective stress and in y-axis it is shear stress, and the shear strength parameters C and phi are obtained from the best fit straight line through the points. From the figure we can determine that the point at which the mass failure envelope reaches the y-axis from 0 to that point it is denoted as C, and the angle made with horizontal is marked as phi. Advantages: the test is simple and quick, and the apparatus is cheaper. No need of technical skill, and thickness of the sample is very small, hence drainage does not take much time. The disadvantages are: the failure plane is predetermined, that is, we consider as a horizontal failure plane, which may not be the weakest plane. The drainage conditions cannot be controlled and no mechanism to measure pore water pressure. Hence, the test is not suitable for fine-grained soils. The test is useful only for freely draining soils like sand. There are stress concentrations at the sample boundaries, leading to non-uniform shear stress distributions on the failure plane. Disadvantages continued. The direction of the principal planes is not known at every stage of the test. It is only after the move failure envelope is known that the magnitude and the direction of the principal stress can be determined. In fact, there is a rotation of the principal planes between the start of the test and the failure of the soil. As the test progresses, the area under the shear gradually decreases. The connected area at failure should be used in determining the values of normal stress and shear stress. This is the arrangement for direct shear test, and in this figure we can see that the proving ring and the square box, that is called a shear box, and in the longitudinal direction we apply the shear force and the soil sample will get sheared and the value can be, or the number of divisions can be measured. Second one is shear strain versus pore pressure. Similarly, here the upper curve shows for loose sand and the negative curve goes for dense sand. Advantages: The test is simple and quick, and the apparatus is cheaper. No need of technical skill, and thickness of the sample is very small, hence drainage does not take much time. The shear strength of sand is due to interlocking of molecules and friction between the molecules. In dense sand, interlocking resistance is 20 to 25% of total shear strength. On shearing, interlocking of molecules breaks and loss in shear strength is recorded at a strain of about 4 to 6%. Where in case of loose sand, interlocking resistance is negligible and peak failure is not recorded. In loose sand, failure is assumed to occur when strain reaches to 20% or more. Next one is the shear strain versus void ratio graph. So here positive curve shows loose sand and negative curve represents dense sand. At larger strain, both initially loose and initially dense specimen attain nearly the same void ratio, at which further strain will not produce any volume change. Such a void ratio is usually referred as the critical void ratio. If void ratio of soil, that is E greater than E naught, the soil is classified as loose soil, and if E less than E naught, then it is called dense soil. Thank you. I hope you enjoyed this section. We will see in the next section. Thank you so much.